Have you ever written a piece of code and you just get that feeling that it's a little fragile? Where you're afraid that making one tiny change might bring the whole thing crashing down? Well, in this explainer, we're going to dive into how to build software that's not just functional, but flexible, strong, and truly built to last.
Let me put it this way. Good software, it's like a well-designed building, right? You can add a new floor, maybe knock down a wall to renovate a room, and the foundation stays solid. Bad software, that's a house of cards. You try to move one card and the whole thing just collapses into a mess. Our goal here is to be architects, not just card stackers. So, how do we get there? Well, the blueprint for this kind of rock-solid software is a set of ideas known as the solid principles. Now, all 5 are super important, but today we're going to zero in on 2 of the most powerful ones for creating flexible, adaptable systems, the I and the D.
So here's our game plan. We're going to start by looking at what I call the forced-to-fit problem and see how something called interface segregation is the perfect fix. Then we'll tackle the rigidity problem and learn how inverting our dependencies can basically set our code free. By the end, you're going to have 2 brand new tools in your belt to build code that really stands the test of time.
All right, let's get into it. Our mission is clear: build software that lasts. So let's kick things off by digging into a really common problem that gets in the way of that. This one. This is a classic headache for developers. It's what happens when we try to create a one-size-fits-all solution, and we quickly find out that, well, it doesn't really fit anyone perfectly. Let's look at a real example. Okay, so check this out. We've got an interface for a parking lot. An interface is basically just a contract, right? It's a set of rules that any class calling itself a parking lot has to follow. And at first glance, this seems fine. It lets you park, unpark, get capacity, but look closer. It also forces you to handle calculating fees and processing payments. It's trying to do the whole shebang. And this is where our perfect one-size-fits-all model starts to crack. A new request comes in. We need to model a parking lot that is totally, completely free. Now what?
This is where things just get weird. To create our free parking class, we are forced by the contract to implement those payment methods. I mean, we can fudge it for calculate fee, just return 0, no big deal. But do payment? What are we supposed to do? The only logical thing is to throw an error, because the whole idea of payment doesn't even make sense in this context.
And here's where it gets dangerous. If some other part of our application accidentally calls due payment on our free lot, boom, the whole program crashes. We've been forced to write code that isn't just pointless, it's a ticking time bomb. This problem has a name, and it's perfect: interface pollution. We have polluted our nice, clean, free parking class with methods it has absolutely no business knowing about. So how in the world do we clean up this pollution? Well, we follow the I in solid, the interface segregation principle. And it's all about making smaller, more focused contracts. The principle is actually really simple when you break it down. A class shouldn't be forced to depend on methods it doesn't use, period. So instead of one giant, bulky, do-everything interface, we should always prefer smaller, more specific ones. It's all about precision. And the process for doing this is super straightforward. First, you just look at your big, bloated interface and find the separate jobs it's trying to do. For us, that's obviously parking versus payment. Second, you create a new, dedicated interface for each of those jobs. And finally, your classes only implement the interfaces they actually care about. That's it. And here is that solution in action. We've taken our one parking lot interface and split it right down the middle into 2. Parking operations for the physical job of parking cars and payment processing for handling the money. Each one is small, focused, and does one thing really well. And just look at the result. Our free parking class is now beautiful. It's simple. It only implements parking operations. There's no more confusing payment logic, no more forced error throwing, no more pollution. The code finally reflects reality, which makes it safer and so much easier to understand. That right there is the power of ISP. Okay, awesome. We've solved the pollution problem. But there's another really common issue that can make our code just as fragile, and that's rigidity. This is when your code is so tightly wired together that changing one piece feels like performing open-heart surgery on the entire system. Now, to really get this, we need to think about 2 kinds of code. You have your high-level modules. This is your core business logic, the what and the why of your application. And then you have low-level modules. This is the nitty-gritty stuff, the how, like the specific details of talking to a database or connecting to a piece of hardware.
So here is a perfect example of that rigidity problem. We have a high-level computer class, but notice what it depends on. It is hardwired to a very specific, very low-level thing, a wired mouse. The computer's main logic is directly tangled up with a specific implementation detail. We call this tight coupling.
And this is where it really hurts. What happens when we want to upgrade to a wireless mouse? Or maybe a trackpad? With this design, we can't just plug a new one in. No way. We have to crack open the computer class itself and start messing with its internal wiring. That is risky, it's begging for bugs, and it is the exact opposite of flexible. The solution to this mess is the D in solid, the dependency inversion principle. Now, I know it has a fancy name, but trust me, the idea behind it is incredibly simple and intuitive. It's all about flipping the direction of our dependencies. Here's the core rule. High-level modules should not depend on low-level modules. Instead, both of them should depend on abstractions, things like interfaces. Think of the abstraction as the contract. The high-level module says, hey, I need something that follows this contract. And the low-level module says, cool, I can do that. And the transformation is just so powerful. On the left, you've got the old, rigid code, but on the right, the new, flexible code. Look, the computer no longer knows or cares about a wired mouse. It only depends on an abstract mouse interface. Now we can plug in a wired mouse, a wireless mouse, a magic trackpad, anything we can dream up in the future, as long as it honors the mouse contract. We've gone from being hardwired to plug and play. Wow, okay, we have covered a lot of ground, from polluted interfaces all the way to rigid, hardwired dependencies. So let's bring it all home and recap the key lessons for writing code that truly lasts. So our two big takeaways. First, the interface segregation principle, or ISP, tells us keep your interfaces small and focused to avoid that nasty pollution. Second, the dependency inversion principle, or DIP, tells us depend on abstract contracts, not concrete details, to build flexible plug-and-play systems. At the end of the day, both of these are about creating smart boundaries that give our software the freedom to change and grow. Look, these principles aren't just some academic theory. They are real, practical tools for building better software day in and day out. So the next time you sit down to write some code, just ask yourself, am I building a fragile house of cards that's going to collapse with the next change request? Or am I building an extensible fortress that can adapt and grow for years to come? The choice is yours.